Okay, folks, it's time for the next online lecture, lecture number 24. Today, we're going to discuss waves in matter, especially what happens at the interface of two different types of matter when a wave hits it. What happens when a wave hits an interface? Then we have the law of reflection, Snell's law, and the Fresnel equations, and this is what we'll be discussing today. So first, let's just say a few words about what happens when an electromagnetic wave travels through matter. We remember our familiar situation. What we did before is what we understand is when waves travel through a vacuum. Now, for a vacuum, we have no free charge, no free current, and we also have no bound charge and no bound current. And so then we know what happens. This is our familiar situation. We have del dot E equals 0, del dot B equals 0, del cross E is equal to negative dB dt. This is our familiar equation, Faraday's law, and Ampere's law. Del cross B is equal to mu naught epsilon naught dE dt. So these are the Maxwell's equations in vacuum, and we know that they lead to a wave equation. And so we can get that the second derivative with respect to time is of either E or B is equal to the second derivative with respect to space of E or B. I guess I should try to write it shorthand. And then there's a proportionality constant, which is the velocity squared, which is 1 over mu naught epsilon naught. Okay, so that's the wave equation that we've been studying already. And so, but now in a material, it's a little bit different, not too different, just enough to be interesting. And so here, let's consider a material, a typical material where there's a special material. Let's consider an insulator. And in an insulator, there's a dielectric, there's no free charge, and there's no free current, because it's an insulator. But you do know that we can get, so no free charge means, rho free equals 0 and J free equals 0. But we can have bound charge and current. So we can have bound charge and current don't necessarily equal 0. In other words, we can have rho bound not equal to 0. We can have J bound not equal to 0. And of course, there's always that pesky little polarization current, which also might not equal to 0. And so now we have this dielectric. So we have some dielectric. And the question then becomes, how does a wave travel through the dielectric? So there's my E and M wave. And what is happening inside? What is the E and M wave doing inside of the dielectric? Okay, well, that's pretty easy to show because what we do is we just write down Maxwell's equations, and Maxwell's equations in the dielectric are, now in the dielectric we have del dot D is equal to, well, it's actually equal to rho free, but rho free is 0. So that's equal to 0 because rho free is 0. And we always have del dot B equal to 0, even in the presence of matter, because there's no monopoles. And we have del cross E is equal to negative dB dt. And that one was unchanged in the presence of matter. But Ampere's law looked pretty different. That's the one we had the most changes, because now Ampere's law is in matter is del cross H, is equal to the time derivative of the d field, d dt. And remember, we had here we had plus j free here, but because j free equals 0, then we can knock this part off. And so this is Ampere's law, del cross H equals d dt of d. Okay, and so these are our Maxwell's equations in a dielectric. Here, I'll circle them. And so the question is then, do these Maxwell's equations support waves? Maxwell's equations in matter. And they do, and it's really easy to show. Let's consider the simplest case is linear material. And this is the only case that we'll discuss. Well, actually, I sort of take that back. Let's just consider the simplest case, linear material. For a linear material, this is the main case that we'll discuss. And so for a linear material, we have D is equal to epsilon E, and then we have H is equal to 1 over, what happened here? Sorry. Actually, a student told me how to deal with this, but I didn't implement it yet. H is equal to 1 over mu B. And then, and so what we can do then is we can plug it in. We can plug it in into these Maxwell's equations. So we plug those guys in, and then we see that Ampere's law becomes rather simple, because we see that the Ampere's law was the most complicated one. Del cross H equals d dt. This is the only one that was sort of pretty different. I mean, because if d equals epsilon E, then we see that the del dot D equals 0 turns very quickly into del dot E equals 0. But the Ampere's law is the more tricky one. And so this one we get del cross 1 over mu B is equal to epsilon dE dt. But then I can just pull this mu over to the other side, and I see that we get del cross B is equal to mu epsilon dE dt. And that's really nice, because now we see that the Maxwell's equations, because we still have del dot E equals 0, and we see that then what we see is that the Maxwell's equations are the same. Maxwell's equations are unchanged from the vacuum case. They're unchanged, except, there's always an except what happens is we just replace epsilon naught with epsilon and mu naught with mu. Because you see here in Ampere's law, we see that this used to be mu naught epsilon naught, but now it's mu epsilon. And so all the effects of the material are living in here. So that's the effect of material, is living in those constants. And that's sort of a trivial result, but it's very profound and very important. And you can see that very easily by simply remembering that the speed of light, the speed of the electromagnetic wave, the speed of the wave in vacuum, and you know that's an important number, the speed, the velocity in vacuum, which is c, is 1 over square root of mu naught epsilon naught. But now, in a material, it's different. The speed of light changes. Oh my God. Because now we see that the v is equal to 1 over square root of mu epsilon. Because everywhere in the old equations I saw a mu naught epsilon naught, I replace with mu and epsilon. And now let's think about that for a minute. That's very profound, because in a typical material, we have epsilon is equal to epsilon naught 1 plus chi epsilon, the electric susceptibility, and mu, the magnetic permeability, is mu naught times 1 plus chi m. And typically what we have is epsilon is greater than epsilon naught. You see, because we have the polarization. And so mu is typically greater than mu naught, typically. And so that means then that the velocity in the material is typically less than the velocity in vacuum. So the speed of light slows down. So light slows down. Oh my God. And that has huge consequences. Light slows down. So we can write the velocity of the, what we like to write is, let's consider the ratio of the velocity of light in vacuum divided by the velocity of light in material. And that ratio is special. We'll give it it's a name. It has a name. It's called N. And that is the, you know what that is? It's the index of refraction. And now we can write it, because the velocity in vacuum is 1 over square root of mu naught epsilon naught, and in the material, it's 1 over mu epsilon. And now, because it's in the denominator, I flip it, and so we see that the ratio of those velocities is mu epsilon over mu naught epsilon naught. And that is so important. We give it a name. It's called N, and that's the index of refraction. And that's very important. Index of refraction. Let's spell it all out. Index of refraction. And so now this is very important. It has huge consequences. The fact that the velocity changes has huge consequences, and the most important consequence is that this gives us lenses. So we can then focus light. We can use this to focus light. And we need that, because otherwise we couldn't take pictures and we couldn't see, or at least a lot of people who wear glasses like me can't see without lenses. And so this change in velocity allows us to focus light. And you will see that in a few minutes. So let's talk then about what happens when light hits a lens. So, for example, you guys have seen this before. You've seen geometric optics. So, geometric optics, you've all seen this before, and you know that when I have a lens, then the light comes in and it gets focused. Oh my God, it gets focused. You know that. To the focal point. Give a little F. But what we're going to do now is let's consider but how does this happen? How does this happen from the perspective of Maxwell's equations? Like, how do Maxwell's equations cause this to happen? Because with Maxwell's equations, we have waves. Oh my God, there's a wave. And we know that there's an E field that's going up and down and up and down. And it's flowing in this direction. There's waves. And then now the wave has changed direction. Why would the wave change direction? And so I can ask that question. Why do waves change direction? Waves change direction. So this is what we want to understand. And also, what is the transmission through a lens? How much of the wave can get through the lens? What is the transmission? How do waves change direction? How much gets through? These are important questions. Let's answer these questions now. So to answer these questions, we need to use Of course, Maxwell's equations. And so that's what we're going to be talking about right now. And so let's draw the situation first. Let's draw sort of the more, we want to understand what happens when waves hit lenses from the perspective of Maxwell's equations. And so let's consider what's happening right at the interface here. Let's zoom in on that region of the lens. And at that little tiny region, the lens is flat. So let's not worry about big curvature. Let's consider first a flat interface. It's the simplest one, and it's pretty general. Consider flat interface. Sorry for being messy. I just can't help myself. So here's the flat. Okay, so now we shoot in the wave at a flat interface, and this is what it looks like. We have a flat interface. I'll call that z equals 0. So this is the z direction. And the interface is between two different materials. I'll call them, oops, sorry, stupid thing. I'll call this interface 1 and interface 2. Now, what determines two interfaces? Well, why are they different? Well, the way they characterize them is with index of refraction. So when I say two interfaces, I mean two materials that have different indices of refraction. And I will use n to denote the index of refraction. So that's two materials, so there's an interface between them. And so now let's shoot a wave at them. Now this is just a guide to the eye, just a dashed line. But here's my wave. So let's first shoot the wave so this is the incident wave. And so I'll call that K sub I. And this wave is coming like this. And so here the wave is up, down, and that's the electric field. And so the electric field, can be written like this. There's some constant polarization, E sub I, E to the I, Ki dot R minus omega t. So that's the incident electromagnetic wave. And so here I'm drawing the little E fields. See, I'm drawing them there. And now it's coming in at some angle. I'll call that the angle of incidence, theta sub I. And then there's going to be some reflected wave. And let's get that reflected wave. So there's my reflected wave. And this I'll call the angle of reflection. And this is the normal. This is the normal direction. The dashed line is normal. The normal direction, perpendicular to the surface, to the interface. And then here's my reflected wave. Let's draw it. So there's some reflected wave. And that is coming out at some K reflected, has some wave vector. And then there's some reflected wave, ER, E to the I, KR dot R minus omega t. That's my reflected wave. And then there's a transmitted wave. Oh my God, transmitted wave. Yay. There it is. My transmitted wave. And that is coming out at some angle of transmission. And the angles are always measured with respect to the normal. That's a convention, and it's important to remember. And here's my transmitted wave. Draw it. And the transmitted wave, there's an equation for it. That's the transmitted wave, the expression for it, e to the I kt dot r minus omega t. And so and I'm only drawing, and here I'm just drawing the electric fields in this drawing, but we remember that the B fields I only draw the electric fields here this time because we remember that the B fields are easy to get from the electric fields, because for a plane wave, and we're only talking about plane waves, I should say plane waves, then I know that the B field is equal to 1 over C times K cross E for a plane wave. So once I have the E, I got the B. So it's okay. That's why we can ignore the B for now. The B follows E. Okay. And so now what we want is we want to know the relationships. This is what we want. What is the relationships between these quantities? EI, ER, ET, as well as KI, KR, and KT. What are the relationships between these 6 quantities? And the typical situation is that you're given an incident wave. So typically the incident wave is given, because that's like your flashlight or your laser. You're given the incident wave, EI and KI. So that characterizes the incident wave, but you want to know what happens. That's what physicists want to know. It's like if I shine my laser beam on some material, what does it do? So what we want to know is the magnitude of the reflected wave, the magnitude of the transmitted wave, and the direction of the reflected wave, and the direction of the transmitted wave. What are these things? So if we're given the incident wave, if we're given this, then what are these guys? That's the typical problem. And so that's what we need to figure out. So let's do it. And that's what we're going to do. That's today's discussion. And so how do we do it? Well, you know the answer. Maxwell's equations. Yay. We use Maxwell's equations. And so let's write them down. But now we have to write them down in a matter, and for matter, and we have to know what's happening at the boundary. So what does Maxwell's equations tell us about the interface? Basically, it's the boundary conditions. So we have to figure out the boundary conditions for the wave. And that comes from Maxwell's equations. And we derive, you remember that we derived all that boundary condition stuff earlier in this course. Now is the shining moment. Now is when it's become most important. All that boundary condition stuff is going to be used here. So let's write it down. So here it is. We know that the boundary conditions are, there's 4 of them. We know that, I'll write them in all generality, but then we don't actually use all of them, but some of them well, it depends on the situation. Let's write them all down. So we know that the D field on one side of the interface, I'll call that D1, the perpendicular component on one side minus the perpendicular component on the other side is equal to sigma free. That's the free charge density, and we've done that before, and that comes from, remember that came from del dot D is equal to rho free. That led to this. Okay, so now the second one is B1, the magnetic field, the perpendicular component of the magnetic field on one side minus the perpendicular component of the magnetic field on the other side is equal to, you guessed it, 0. And that came from del dot B equals 0. We derived it. And then the third one is E1 parallel, the parallel component of the E field on one side minus the parallel component of the E field on the other side is equal to 0. And you know that one comes from this, del cross E. When we originally did it, we had del cross E equals 0 for static, but it's still true here because now we have del cross E is equal to negative dB dt, and this goes to the flux, but the changing flux goes to 0 for a tiny loop. And so when you do the same derivative, the same derivation, you get the same answer because, and go through it and you'll see, you get the same answer. So then we get the parallel component of the E field is the same on both sides of the interface. Then the fourth one is going to be the parallel component of the H field. H1 parallel. Oops, I won't put the parallel up there. H1 parallel minus H2 parallel is equal to K free. If there's some current density flowing on that interface, K free cross N. And we got that from Ampere's law. We know that one, right? Del cross H equals J free. Okay, so all right. So these are our boundary conditions, and so, but for the case of but now let's consider them for the case of a dielectric, because these are quite general boundary conditions I've written. But for a dielectric, there's no rho free, and there's no J free. And so for a dielectric, then we see that this one, number one, equation one, can be rewritten as epsilon 1 E1 perp, because that's what D1 perp, right? Because D equals epsilon E, right? And so I can write that epsilon 1 times the epsilon 1 E1 perp is equal to epsilon 2 E2 perp, and this equation becomes the same equation, B1 perp equals B2 perp, and this equation doesn't change either. That's an easy one. E3, oops, 3, where did that come from? E1 parallel is equal to E2 parallel. And then the fourth one also is fairly simple, because this will turn to 0, and we have B, for a linear material, B1 parallel over mu1 is equal to B2 parallel over mu2. Okay, so these are the boundary conditions for the perpendicular. I kind of screwed that up. Let me get rid of this. Okay, these are the boundary conditions for a dielectric here. The B boundary conditions, and this is what we'll use to figure out how the waves bounce off of a lens, of a dielectric, of an insulating material. And so let's do it in steps. And so so remember, the whole purpose of this is to figure out what is going on here, right? This situation. That's what we want to figure out. What is going on here? Okay, so let's figure it out. And so let's first consider this at this. So this is the, sorry for moving this around so much, but this is the boundary condition right here, z equals 0. Whoops. This is the boundary condition, z equals 0. And so we want to know what's happening at that interface. And so at z equals 0, the interface, then let's consider equation 3. And equation 3 is this one. That's the most important one for waves. I'll give it 3 stars. Most important for waves, that one. And so so for equation 3, we'll write it down, and we see that for equation 3, we're going to have, if we go, if we look at this, I keep doing that. Let's just draw the damn picture here. Here's the interface, z equals 0. And here's my incident wave. Here's my transmitted wave, K transmitted. And so I'll call that E incident. And this one is E, not transmitted. I'm sorry, that's reflected. Whoops. And then this is my thing. And then this is my transmitted wave. And it looks like that. And that's E transmitted. Okay, that's the situation. And so we see that from equation 3 that we're going to get that E1 parallel plus E2, I'm sorry, on side 1, what we have, side number 1, we're going to have E incident parallel plus E reflected parallel equals E transmitted parallel, because that's on side 2. Because this comes from the fact that E1 parallel equals E2 parallel. And so on side 1, we have two waves, the incident and the reflected, but on side, this is side 1 and this is side 2. On side 2, we only have one. So that means that we have that the parallel components on the left side must equal the parallel components on the right side. So that's left side, right side. So let's write that down in equation form. So we can write that as an equation. E incident, actually I need room. E incident parallel on the left side is a wave, e to the I, ki dot r minus omega t, plus the reflected, ei k reflected dot r minus omega t is equal to the transmitted wave. Transmitted, e to the I, kt dot r minus omega t. And these are parallel. These are the parallel components. Okay, so this is what we get from equation 3, and this is really important. So now let's divide out the time part, and we can do that because all the waves have the same frequency. All waves. When I say all waves, I mean the incident, the reflected, and the transmitted wave have the same frequency, have same omega. And so I can just divide it out, dink, 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 and then that leaves us with this new equation, which is very important. EI, the parallel component, times e to the I ki dot r plus the reflected parallel component, e to the I k reflected dot r is equal to the transmitted component, the parallel transmitted component, e to the I k transmitted wave vector dot r. Now, so this is a really important equation. This has to be true. And there's a lot going on in this simple equation. It's just basically saying the left side equals the right side, the parallel component on the side on the left equals the parallel component side on the right at the interface. And this is all at the interface. Z equals 0. And so now let's notice a few things from this important relationship. Notice some things. And the first thing that we notice is that something I already said, but which is that the frequencies are the same. I just want to emphasize that the incident and reflected and transmitted frequencies are all the same frequency. So that's the same. Frequency is the same. And that kind of makes sense, though. Why would the interface change the frequency? Think about it. But if the frequency is the same, then that leads to something very interesting, because we know that omega is equal to kV for a plane wave. We know this to be true. And so that means then that if the frequencies are the same, then that means that these products are the same. Ki Vi equals Kr Vr equals Kt Vt, because this is just omega I, and this is just omega R, and this is just omega T. And so that's very powerful, because then we immediately see, we realize that we have for side 1, on the incident side, we know that the velocity of the incident wave has to equal the velocity of the reflected wave, because it's the same material, since V is equal to 1 over square root of mu epsilon, and mu and epsilon are the same for the reflected and for the incident and reflected wave. And so then that means, though, then that if Ki Vi equals Kr Vr, and if these two things are the same, then that means that Ki equals Kr. And that's sort of obvious in a way, but it's still important. And that's just basically saying that the wavelength is the same, since K equals 2 pi over lambda. So that makes sense. The wavelengths. So the wavelength's the same. Wavelengths same for incident and reflected wave. Okay, that's not too profound. But now let's look at the transmitted. And so now we go to, we see that for side 2, then we see for the transmitted wave, we see that the Kt Vt is equal to Ki Vi. And so that means then that I can write the incident wave, Ki, the incident wave vector magnitude, is equal to Vt over Vi times Kt. And that's a relationship between the incident and transmitted wave vectors. And we know that the ratio of these velocities, the V transmitted over the V incident, is going to be simply equal to the index, wrong thing there. It's simply going to be equal to the index of refraction on the incident side divided by the index of refraction on the transmitted side, N1 over N2. And so that then tells us that Ki is equal to N1 over N2 times Kt. Okay. And so that's going to be useful a little bit later on. So that's a simple relationship that we get. So that's the first thing we notice, and that just comes from the frequencies being the same. So that's kind of cool. But now let's notice something else. Number 2, this is the second thing we notice. And remember, this is all coming from this equation here. This is the important equation where we get a lot of information. This boundary matching at the interface. And so another thing we notice from that equation is that if we if we look at that equation, I don't want to draw the equation again. So let's consider equation. Let's consider the equation at interface for r not equal to 0, where r is parallel to the interface. And so what I mean by this is that let's consider this equation, and then let's consider what happens. I have a feeling I'm going to have to redraw this equation. I can't keep going up and down like this. Sorry, I'm going to just have to draw it again. So this is the equation. So we see that the parallel component of the incident field at the interface multiplied by this phase factor plus the parallel component of the reflected wave multiplied by this phase factor is got to be equal to the parallel component of the transmitted wave multiplied by its phase factor. And this all, remember, this all came from this very simple one that we derived, that E1 parallel equals E2 parallel. So this all comes from a very simple relationship, but it leads to this funky relationship between the three different waves, the incident, reflected, and transmitted wave. We see that we have this very important relationship. And so now that's what we're going to do is, let's consider this equation at z, at the interface, z equals 0. And then the way to think about it is, like, if this is the interface, let's think of this as this is the plane of interface, I'll call it the boundary, plane of the boundary interface. And let's put a coordinate system here like this. And so I'm going to rotate it a little bit. I have a reason for doing this, so don't be too freaked out. But I'm going to call that vertical guy X and the horizontal guy Y. Now let's just consider this vector. Let's just consider this vector, some vector R on that interface. And that's going to be this vector right here. Now, because the thing is, I can put my origin anywhere. So I'm going to say, put the origin in the interface, like I did, at the center of the interface, like I just did. And then there's something to notice. Now consider what happens at the center of the interface. Let's consider R equals 0. And so then I have EI parallel plus ER parallel equals ET parallel. Because what happened then is that the phase is 0. Phase factor is not the phase factor, the phase itself, I'm sorry. The phase K dot R is equal to 0. And e to the I0 is 1. And so, okay, so the phase is 0. But now start moving away. Try moving away from 0. Try moving away from 0. And then the phase factor oscillates. Phase factors oscillate. E to the I, K dot R. They oscillate. That's what a wave is. And so we see even at the, and here they are. Here's the three phase, here's these phase factors here, here, and here. These three phase factors oscillate as we move away from the origin. They're oscillating. And so what happens then is that if I move anywhere on this interface, they must, for this equation, I'll call this equation asterisk. If my equation is true, for equation asterisk to be true, everywhere on the interface, and this is a profound statement, everywhere on interface, so this is actually important. I'm not just being pedantic or whatever. For this to be true everywhere on the interface, then the phase factors must oscillate the same. They must oscillate let me write it out. They must oscillate the same. Phase factors must oscillate at the same frequency. Oscillate at same spatial frequency. And that's a profound statement. If that is obvious to you, then that's great. If it's not obvious to you, then think about it. Because this is a really profound and powerful statement, because it's phase matching. The phases must match. We have phase matching. Maxwell's equations tell us that we must have phase matching at interface. And that must be true, because I have these three phase factors. I'll call them here 1, 2, 3. Those 3 phase factors. And for this equation to be true, equation star, then those 3 phase factors must always be equal. They must be equal at everywhere on the interface. And for them to be equal for everywhere on the interface, how can that be? The only way that can be is this. For this to be true, then the phase factors must be the same. I need Ki dot R equals Kr dot R equals Kt. Let me pull it down a little bit so you can see. Let's try to equals Kt dot. Did that weird thing again. Shit. Looks like my things has flipped out. Okay, there. There's a bug in this program. So the phase factors must be exactly the same for these 3 oscillating factors to be the same everywhere on the interface. So I want you to think about that. And that leads to a lot of important physics. And so we're going to go with this, but but there is a way to prove it. If that physical reasoning, if you did not like the reasoning I just gave, then you can prove. You can prove it. And I'm not going to go through the proof. I'm just going to set it up. And anybody who wants the proof, you can email me and I'll post it somewhere. If you want to see the proof. But here's a proof. Let's turn it in purely mathematical language. If I have this, just some exponential ae to the I ax plus be to the I bx equals c e to the I, that's little cx. And then for this to be true, so to be true for all x, then we need A equals B equals C. And that is basically the math. If this is true, then this is true. And if this is true, then that means that the phase factors are equal. And we can prove it. So you can show that if this equation with the 2 stars is true for all x, then we can prove this. It's a mathematical proof. But if you want to see the proof, ask me by email, because I don't want to go through it now. Okay, but let's just assume it's true for this wave plus this wave to equal this wave, then the phase factors must be the same. And let's assume that that's true. And because then it leads to some very powerful insights that we can notice. For example, we can notice that if we look at the interface, if we consider the interface, or boundary. When I say interface, I mean boundary. If we consider the interface, this thing that I drew before, then if we draw it like this, if this is the x direction, and this is the y direction, and the z direction is going into the page, then you can see that we must have that we must have that the projections of the transmitted the projections of the transmitted, reflected, and incident waves must all be the same. Projections must all be the same. And so the projections of the k vectors, projections of the k's, must all be the same. And that comes from this thing. And you can prove it yourself because look, this is r vector, and I have ki dot r is equal to k r dot r equals kt dot r. And so if I pick any r, just some random r, then the projections of all three of these must be the same. And so that means that the projections for any r, and so then the projections onto the plane must be the same. So the projections of the k's, projections of k's onto interface must be the same, onto interface are equal. Okay, well that's very powerful. And so then what that means is that, but for these projections to all be the same, that means then there's another very powerful consequence, which is that the k vectors must all lie in the same plane. And so the k's, when I say k's, I mean for the incident wave, reflected wave, and transmitted wave, the k's must all lie, in the same plane. And so let's consider, like, let's rotate. Let's see how that works. Let's now rotate our view by 90 degrees from here. Let's rotate it and see what it must look like. So if we rotate that view, then what we see then is that, let's see, can I keep it in the same? No, it's too big. Let's keep it here, and let's consider this. Let's rotate our view. I don't think I want to draw a box here. And if we rotate our view, then this is what we see. We see this. This is we get this famous picture. We see that if I have some k incident, and this is what the way to think about it is, this is what I'm starting. I have a plane wave. This is a plane wave coming in with some incident wave vector ki at some incident angle of incidence, and it's reflecting with some k reflected, and it's a plane wave, and this is the reflected angle, and then this is my transmitted wave. That's my transmitted plane wave, and this is my transmitted angle. And the point is that if I start, this is what we start with. with this guy, but then these two guys, KR and KT, so must be in the same plane. So start with KI, then KR and KT must be in same plane. As I've drawn here, this is the plane. And so this plane is actually, the way I've drawn it for this coordinate system, now this plane is, this direction is the Z direction, and this direction is the X direction, and now the Y direction is coming out into your face. Okay, so and so this plane, so here the XZ plane has a name. We call that the plane of incidence. Because it's the plane, and this is a little confusing because you would normally think it's the interface plane, but it's not. The plane of incidence is the XZ plane. It's the plane that holds the K's. Plane that holds the K's. Whereas it's the XY plane, which is the boundary plane. That's the interface or boundary. And so that difference is very important. So we have these two planes, the plane of incidence and the actual interface. They're different. And here are their coordinate systems. Okay, so we're gonna so this gives us some more insights, because now we see that if these are the K's and they look like that and they must be in this plane, then I can see the projections. And the fact that these lie, okay, the projections of the K's must be equal. The projections of K's on the interface must be equal. We talked about that before. Must be equal. And so from this picture, that tells us then that K, I, X, the X component, according to this coordinate system, of the incident wave vector must equal the X coordinate of the reflected wave vector, which must equal the X coordinate of the transmitted wave vector. And so then now I have all these angles, and so this then tells me that the X component is going to be Ki. The X component of the incident wave vector is Ki sine theta I, has to equal the X component of the reflected wave vector, which is Kr sine theta R, equals the X component of the transmitted wave vector, Kt sine theta T. And this is all coming from that phase matching condition. So this is really profound. This is really big deal. And so then let's consider, so from this, and this came from the phase matching consideration, let's consider the first two. Let's consider this equation. So let's consider on the region 1, in the left side, because remember this is region 1 and this is region 2 on the interface. And so let's consider the left side of the interface, in which case I have Ki sine theta I equals Kr sine theta R. Now we know that on the left side, Ki has to equal Kr. We derived that already. And so that means that sine theta I equals sine theta R, and so that means that theta I equals theta R. Oh my God, we just derived a really important thing. This is called the law of reflection. And you might already, I'm sure you already know this law. Of course, we all know it from experience, but the incident angle is equal to the reflected angle measured from the normal. And this is a very profound law of nature for waves, and it comes from the phase matching condition. So we just derive the law of reflection. That's how you derive it. And then there's another profound law that we can derive. Let's now look at these two. Let's relate region 1 and region 2. And so when we relate region 1 and region 2, we can see that Ki sine, actually it's not this one. It's going to be this one. Let's relate these two. And so when we do that, we see that Ki sine theta I is equal to Kt sine theta t. And then what we can do is we can now use our little trick, because we remember that Ki is equal to n1 over n2 kt. Remember, we derived that before. Now we'll just plug it in right there. And so then what we'll get is, we'll get that n1 over n2 kt sine theta I is equal to kt sine theta t. So now these guys cancel, and we end up with this very famous relationship. And I'll call this I, I'll replace with a 1, and t, I'll replace with a 2. And then we end up with n1 sine theta 1 is equal to n2 sine theta 2. And this is, of course, Snell's law. And so this is a really, you guys have all seen this before, and so you can see how Maxwell's equations lead to Snell's law. And also Snell's law is really coming from the phase matching of the waves. Phase, I'll just keep repeating this. The law of reflection and Snell's law come from phase matching of waves, of the incident, reflected, and transmitted waves at the interface. And that's the most important insight here, is where this all comes from. Okay, so we got these nice relationships, and these relationships are really nice, because basically what this is telling us is that if we're given the incident wave vector, which is basically described by the magnitude and the incident angle. That describes the vector. That gives us the magnitude and direction. Magnitude plus direction of the wave vector. Then, if we're given that, then we can easily find Kr, which is Ki and theta, Kr and theta r, and we can easily find Kt, which is the magnitude and the direction. So we know how to get from Ki, then we know how to get Kr and Kt. We know how to do that using Snell's law and the law of reflection. Okay, good. But what we don't know is this. If we're given, suppose we're given the amplitude of the electromagnetic wave, EI, then the question is, what is ER and ET? ET, phone home. What is the amplitude of the reflected and transmitted electric field if we're given the incident? So this is the one that is not obvious. So we got the K's, but what are the E's? All right, so then let's answer this question. So let's answer this question. So let's find what the reflected and transmitted waves are. And let's do that right now. the amplitude of the reflected and transmitted electric field. And so and let's do that. Let's find them, and let's do it in terms of. Remember what we're given. We're going to do it in terms of the incident wave. So this is what we're given. We're given this, and we want to find these guys. Okay, so how do we do that? This is what we do. This is called, to do this, what we're about to derive are called the Fresnel equations. That's what the Fresnel equations are. They relate the transmitted and reflected electric field amplitude to the incident electric field amplitude. And so let's figure out what they are. So let's do it. So let's draw this drawing. That's my interface. And I will just say, first I will just say, we're going to derive it for the electric field parallel to the plane of interface. There's two situations. I can have the electric field parallel to the plane of the interface, or I can have the electric field perpendicular to plane of interface. These are the only two cases that matter, because any other case can be just a superposition of these two cases. So there are two cases, and let's do the one that the electric field parallel to the plane of interface, and for the electric field perpendicular to plane of interface, that's for homework. Okay, so right now I'm going to do the one case. So these are the two cases. Actually, let me make this a little bit more formal maybe. So we have one case A, and we have case B. And today we will do this. This is case A, but case B will be for homework. So let's draw case A, parallel to the plane of interface. For this case, this is what we have. So here's our boundary, z equals 0. This is the boundary. This is material 1. This is material 2. This is described by index of refraction 1, index of refraction 2. And now let's draw the normal. We'll draw the normal. And now let's draw the wave coming in. That's the incident wave. And now the wave coming out. That's the reflected wave, sorry. And now the transmitted wave. And this angle is the angle of incidence, the reflected angle, and the transmitted angle. Now let's draw the electric fields. And so here's the electric fields. Let's suppose that that's my incident electric field. And that means that we know that the B field must look like that. And the reason we know that, of course, is from that simple relationship between B and E, right? That we've derived before. And then let's draw the reflected wave. So this, you can see that now my incident wave is parallel to the plane of interface. And now I have to draw my reflected. Now notice I could draw my reflected in two ways. I could either draw it this way or this way. I have two choices. Let's just arbitrarily pick one choice. We'll pick this choice. But I just want to emphasize that it wouldn't have mattered if we'd picked the other choice. Because we know that the electric field is perpendicular to the K vector. We know it's perpendicular to the B field. So we really had two choices here. We've just picked one arbitrarily. And I just want to say the math will work out no matter which choice you make. And so let's draw now the B field. So once we have the K and the E, then we know what the B field is, because we know the relationship between them for a plane wave. And now let's draw the transmitted wave. And I have two choices. I could have picked it either this way or this way. but let's just arbitrarily pick this one. And so that's my transmitted wave. And that means then that my B field must look like this. And I just want to point out that it wouldn't matter which one we chose. We'd get the right answer. It's just some signs would have changed. So this is, and here we have the E field parallel to plane. This is the case A, where E field is parallel to plane of incidence. Okay, so now what we have to do is find the relationships between these three things, basically. We want to basically figure out what is ER, what is ET in terms of EI for this diagram. And so we're going to use the boundary conditions. And so let's use, basically this comes from Maxwell's equations, so we'll use the boundary conditions that came from Maxwell's equations. And so we're going to use the two boundary conditions, equation 1 and equation 2. Let's write them down. Equation 1 is E1 parallel is equal to E2 parallel. The parallel component of the E field is equal on the two sides, and also we'll use the fact that the B field, the H field, is the parallel component of the H field is the same on the two sides, and that means that it's the B field divided by the permeability. So B1 parallel divided by mu1 is equal to B2 parallel divided by mu2. We'll use these two equations. So let's, oops, sorry, let me just get this. Okay, and so so these two equations we'll use, and so let's do equation 1 first. So from this diagram, let's do equation 1. So what is E1 parallel? Well, E1 parallel is going to be the incident parallel component plus the reflected parallel component. And from and when we do trigonometry here, we can see if you draw these little lines here, you can see pretty easily, if you think about it. If I draw these little lines here, then you can see that the angles inside these little lines here and here and here, those are the same angles. Those are the incident angle, the reflected angle, and the transmitted angle. I don't have space to draw it all, but it's the same angle. And you can see that from geometry pretty easily. And so that means that EI cosine theta I is the parallel component of the E field. That's the component of the E field parallel to the plane of incidence, or not plane of incidence, the interface, plus the reflected E field, which is cosine theta R, and this is equal to the transmitted, the parallel component of the transmitted field, cosine theta T. And then what I can do is just, I know that these two are the same. And so, because since theta I equals theta R, and so then what I can do is I can divide out by cosine theta I, and so that leads me then to this equation, EI plus ER is equal to alpha ET, where alpha is equal to the ratio of cosine theta T over cosine theta I. Okay, so I have an equation. I haven't solved it yet, but I have a new equation. And so this comes from, so that's equation number 1 that we get from boundary condition number 1. And now let's look at boundary condition number 2. And from boundary condition number 2, we have to look at the parallel components of the B field. Now let's go back to the drawing. And we see, you see the B parallel here. Let's see if I can reproduce it here. Remember I had this picture. I got this guy and this guy and this guy. And from down here I have I, R, and T. So it was I, R, and T. So this is BI, BR, and this is BT. Did I get that right? I, R, and T. Yeah. Okay. And so now if I want to do equation number 2, then I see that on the left-hand side, B1 parallel is going to be 1 over mu1, and the B1 parallel on the left-hand side is the sum. It's going to be BI minus BR, BI minus BR. And you can see that from here, because see, notice how this guy, BI, is pointing up, whereas in parallel to, these guys are all parallel to the boundary, to the interface, but BR is pointing in the positive direction, whereas BR is pointing in the negative direction. So the total parallel component, I have to subtract them. And then on the right-hand side, there's only one component, and he's parallel. So I'll call him 1 over mu 2 BT. So that is equation 2 for this geometry that I've drawn for this electric field parallel to plane of incidence geometry. Okay, and so now let's use this. Let's use the fact that B is equal to 1 over V times E, and we know this to be true for plane waves. We've derived this already, and so that means we can get rid of all the B fields, and so we can write 1 over mu1 times BI. We'll replace that with 1 over V1 on side 1, EI minus 1 over V1 ER is equal to here 1 over mu2 times 1 over V2 ET. Okay, so I just made that substitution. And so then what I can do is multiply times, I'm going to multiply times mu1 V1, both sides of the equation. And then that leads me to this. EI minus ER is equal to this funny thing, beta times ET, where beta is equal to this ratio of mu1 and mu1 it's going to be mu1 times n2 over mu2 times n1. And I got that because remember that n2 over n1 is equal to v1 over v2. Okay, so n2. Yeah, okay, so I use that. And so this... Oh, hold on. Gory! Gory?
Gabriel locked me out.
No, don't bother me right now, Joshua. Okay, so so then we get this new equation. Sorry guys, I could not pause the recording because the iPad does not allow me to pause the recording. If any of you know how to pause the recording, please let me know. I could not figure out how to pause the recording, so I have to just keep going, even when people interrupt. Okay, so now, that was my stupid kid. Okay, so now we get these two equations. And so this equation we get from the second boundary condition. So basically now this is really nice because we have two equations and two unknowns. Because remember the unknowns are, let's remember what's known and what's not known. The unknowns are E, R, and E, T. But we do know EI. So we're given the incident and we want to find the reflected and transmitted. So we have two equations, two unknowns, so just solve them. And it's easy. So just solve them, and that's very easy. Very easy algebra. Solve them, and then what we get is the Fresnel equations, because when we solve them, we find that E R over E I is equal to alpha minus beta divided by alpha plus beta, and we see then that E T over EI is equal to 2 over alpha plus beta. And those are our Fresnel equations. We've solved it. Where alpha is equal to cos theta t over cos theta I, and beta is equal to mu1 n2 over mu2 n1. And alpha and beta are known. Alpha and beta are known. So EI and alpha and beta are known. And so then what we can get is ER and ET. That's the whole point. And so that's what we've done. And so that, I think, is where I'll stop, and we'll do examples of this next time and see some more consequences of this. But this is a good place to stop. Bye-bye.